transactions, but not in a straightforward way by locking rows across databases. So what this CAP theorem eventually implies, especially when you're building a web-based system, is what we call something called base. This is not a very clear classic programming paradigm, but this is where the systems tend to be today. What base literally stands for is your base. The system is basically available. It's scalable, and it's eventually consistent. So you give up certain constraints of what we call a strong consistency. If you are going to write, if you take a user's, if a user goes through checkout and adds a bunch of items, the subsystems that depend on this are not going to get the data read immediately. They will eventually get it, but they're not going to get it immediately. That's the difference in paradigm. And when you're going with this paradigm, you have to build a lot of components, a lot of abstractions to achieve this type of paradigm. But it's not something new. It's kind of it's well known. Even like a DNS is a classic example. If you come up with a new website now, somebody that's logging in, say 500,000 kilometers, like 5,000 miles away from here, is not going to get that site immediately. So, but eventually, the DNS picks it up, the ISPs pick it up, and eventually they're able to come to your site. So it's eventual consistency is kind of a way of life, but you just have to see it see it a different viewpoint, and it's been done before. It happens across us. Like even when you're loading a file, the user doesn't expect the user doesn't expect the image to be seen across everywhere, but they do expect like an experience where, like JavaScript, right? Like you show something to the user that something is happening, but it's still eventually consistent. I mean, eventually it will get there. So one of the fundamental criteria that you have to understand before trying to take any kind of scaling approach is you need to understand your own system. So if you're not able to do any kind of distributed transaction, any kind of uncertainty that you have to build is all managed within the application. So you have to understand how your existing system behaves. So for example, if you have a system where you have 100K users and then you want to scale it to 500K users, you try to simulate your existing system with data that you know. So if your most common use case is a sign-up use case, 80-20 rule applies. So if 80% is a common user sign up and 20% is guest or whatever. So you try to go with your most common use case and try to see if your data models, your data validations, your service interactions really scale appropriately. So if you say you're doing 100K user signups and then you're doing 200K transactions at that point, if you scale that out to 500K, you should see a linear increase to 1 million writes to the database. When you do this type of dissection, sometimes you figure out that you're just doing 800K, or on the contrary, you are doing 1.5 million writes to the database when you should be doing 1 million writes. And what traditionally happens is it's probably a bug in the system, or you figure out somebody is actually doing a better job. Some component is actually doing a better job than what you expect it to be. So this is something what is called a data causality map. You have to build your system. You have to understand what your current systems are before you kind of go out and say, okay, scaling a system is not difficult. We'll just find a cloud provider and then we'll get more web servers, more app servers, and then you're done. It just doesn't work like that. So if your database is your bottleneck, the more you actually scale, it'll actually bring the system down faster. So everything works fine if you're taking to 1 million, and then it works fine till 2 million. But then all of a sudden, when the next customer logs in, he or she brings the whole system down, and it impacts all the current users, the 2 million new users who are using the system. So it's very critical that you have a clear understanding of your existing system. So scaling is just not by running more VMs. It's about your application architecture, your data architecture, the product experience. A classic example is a Facebook like, right? So it's you like it, but you say like, but your friends don't see it immediately, which is fine, and you can live with it. And also the cost. So you have to figure out if you want to eventually scale a system, whether it's really worth spending that much time and money onto it, or you can live with the experience. So even an asset experience is fine for certain parts of the system, right? So for example, if you're doing a reporting application and it goes down, it's fine. I mean, you don't have to really break your head on it. But if it's a customer-facing experience, you don't want to have a bad customer experience. So it's very critical you understand your existing system. Where any cloud provider or any VM stack really helps you is ability to actually validate your current understanding. So if you have difficulty today to scale, to even mimic this type of request, today you can easily go to any cloud provider and increase your VMs and test all this out. So so you should be able to leverage existing utilities to understand your system better. The tricky portion of this is keeping that understanding throughout the life cycle of the organization, right? So today I come up and I come up with the data causality map for the subsystem, and it's very difficult to maintain that map throughout, because things move on, orgs change, etc., etc. People move, so it's very difficult to maintain that. That's the reason not many folks continue to do this throughout the life cycle. Another thing you have to realize is not all data is equal. So this is a critical assumption. So data as it flows through, everybody traditionally has a workflow, right? So user goes through checkout. So there is the user service invocation. There is the orchestration layer that comes in. There is the item, the cart writer, and then there is the inventory, then billing, etc. Right? So, but the same data, transactional data, if you have transactional data that's going through a pay flow, it's not, the user data at that point is not that critical as the transactional data. Like for example, if you want to know the user profile, but for somebody who's going through a pay API call, the user profile data is completely irrelevant. So at that point, it's a transactional data. The user profile data is a good thing to have, but your guarantee to the system is purely on the transactional data. Same thing on the user profile page, right? So if a user comes in and even on PayPal, if they want to see their bank account, their credit card numbers, and all their previous history of transaction, etc., if you show them the credit card, bank account, and then if you're not able to show the transactional history data fully, that's fine. So it's like you have to figure out what data is needed in what flow and build your services around that. So it's not like a single shot solution for everything. It depends on the workflow that you are in. And also, this is something not many engineers tend to focus on. You have to figure out what is your data retention policy as it applies to your org, etc. The reason for that is you want all your SOR, the system of truth record, to be probably in a good database like Oracle or MySQL or any kind of relational database, right? That gives you strong asset properties. But then the SLA around those data is what drives every behavior, right? So if, for example, users are a lot more interested in 2 months of data traditionally compared to 2 to 24 months. And for example, and my interest in any data that's greater than 22 years is really less. So maybe for compliance you have to hold some data, but that doesn't mean that have to be in your current system. I mean, the SLAs are different. So even if an auditing body is going to come to your org, you don't have to like give them like within 50 milliseconds 7 years of data. That's not the expectation, right? So, but within 50 milliseconds, you have to try, for a user who's going through a transaction flow, you have to satisfy the pay API. So you have to figure out like what type of data you're doing, what type of data retention you have, and how you build your SLAs around it. And this impacts because anytime you spin a disk or anytime, even to read, and then when you're spinning disk to write, your SLAs are way off. So you have to understand how data comes around your SLA. So you have to do this kind of homeworks to, you have to do all this type of homework to set the SLAs in the first place. So some of these things you don't even need anything. Like all you have to do is to trim the data around, and then you're good to go. Your SLAs that were like, like 300 millisecond comes down to 100 millisecond just because when you're writing your indexing and then the index is building, the size of the table is so large, the index tends to be large as well. But the moment you start trimming it, things tend to be faster. So understanding these type of requirement actually drives a lot of factors around your SLA, the data, the way you want to replicate data, whether you want to normalize or denormalize data for that particular use case. All this is driven by your existing behavior and also the understanding that all data is not equal. So if you're normalizing and then you're joining like 8 tables together to do a write, you're probably hosted. So at that point, you have to figure out how to denormalize your data, do one write someplace, but then eventually when it goes to your system of record, it's very consistent. And of course, there are techniques that you can do like partition of your data, sharding of data. I mean, they do have their own advantages and disadvantages. So like user profile data, you can probably shard it, and then based on the user account number, if you have 10 shards, so probably based on the user account number, you go to a modulo 10 and then go to shard 1 or shard 2 or shard 3, whatever. Right? So there are techniques of data sharding, and people do apply this at a wide level as well. So if you are a Facebook user, you probably have friends who are probably a lot more closer in your geography compared to somebody across geography, right? So you can use those kind of techniques as well. So if I'm out of Chennai, there's a good chance most of my network is out of Chennai. If you're out of Delhi, most of your network is out of Delhi, and then there are a couple of users who probably are not out of Delhi. So if you're planning to do a data center for such type of applications, you probably try to say, okay, just to minimize round trip, these type of users go into the Delhi data center compared to these kind of users who go into another geography data center. But then you still have to do certain amount of golden gating, replication of data, etc. But then your core customer experience is not compromised because your reads tends to be faster. Most of my friends are probably within my area, so when you're building the graph, it's a lot easier to build that graph also. So it just any type of example you can take it and drive the user experience around it. So now we come down to some of the core principles of scaling a general system.